So last week? What did we talk about last week?
Ionic bonds.
Oh, the bonding, yes, bonding. So now we know what our compounds are named, how we write them. We know how they're held together. We know the bonding, the valence electrons, the Lewis dot structures, the shapes, things like that. Now we're going to start doing things with our compounds. Okay? And before we get into actually doing reactions with our compounds, we have to start to classify our compounds and put numbers with them. Because when we get into our reactions, we're going to have a lot of numbers. From here on out, we're going to have a lot of math. Okay, at least until the last couple weeks of the semester. It's not going to be hard math, but it's going to be more and more math. So the first way that we can describe a compound mathematically is something called percent composition. And all it does is it tells us what percent of the total mass of a compound comes from each individual element. Okay? So what we're going to do is we're going to take the mass of the element we're looking at, how much mass of that element is in our compound, and divide by the total mass of the sample. Multiply by 100, and that will tell us what percent composition that element is. So, if I have 100 grams of sample, and I tell you that there are 50 grams of carbon in that sample, what is my percent composition of carbon? You can do that math in your head. 50, exactly. 50 grams of carbon divided by 100 grams of sample times 100 is 50%. It's half carbon. That's all that's telling us. So here is an example of the type of problem you'll see. So we have 3.67 gram sample of a mineral called chalcopyrite, and we figured out that in that sample there are 1.27 grams of copper, 1.12 grams of iron, and 1.28 grams of sulfur. We have to figure out what is the mass percent or percent composition of each element in that compound. So we're just going to take the mass of an element, divide by the total mass, get that percentage. Move on to the next element, and then do the third element. So let's start with copper. What is the mass copper that we have? 1.27 grams of copper. I'm going to divide by the total mass. What is the total mass? 3.67 grams. What is that?
346,049.
34.6.
0.346, and that is 34.6%. So multiply by 100. Iron, do the same thing, get 1.12 grams of iron divided by 3.67 grams, and that equals what?
30.5%.
And then when we get to sulfur, we go 1.28 sulfur grams equals what?
34.9.
4.9%. When you add them up, they should equal 100. If they don't, something is wrong. Yep. Yes?
What about if it's roughly 100?
I mean, if you come up to be 99.9, then that's just a rounding thing, and don't worry about it. As long as you have the right number of sig figs, you'll be okay. So that is calculating mass percent. That's not hard, right? You can do that. Remember, it has to equal 100. So, Once we calculated that one and that one, we didn't have to calculate sulfur the same way. We could have just gone 100 minus that minus that. It would have given us the same number. If I had a different chunk of chalcopyrite, would the mass percents be the same or different? Got one different. Got one the same. Why do you say different?
Because then you would be dividing by a different amount, so the percentage would vary.
Why do you say the same?
Because if you had more of it, then the other parts of it would just stay the same, it would just get bigger.
Are you asking if the total end result is always going to be the same?
That the percentages, yes.
So wouldn't it always be 100? Or is that what?
Oh, if I had a bigger chunk, would sulfur always be 34.9? Would copper always be 34.6? If I had a chunk that was twice as big, okay, that number is going to be twice as big. But I'm also going to have twice as much copper, and twice as much iron, and twice as much sulfur. And so the fraction stays exactly the same. Mathematically, if I do the same thing to the top as I do to the bottom, the fraction doesn't change. It's just like the density question that everybody, well not everybody, well, most people who actually answered the question on the post-lab got wrong. Most people completely skipped it. It said if you have a block and you cut it in half, now what is the density? Most people completely skipped that part. But most of the people who answered it got it wrong. Density is intensive. If you cut the block in half, yes, you have the volume, but you also have the mass. So mass over volume didn't change. Same thing here. If you cut double that, the fraction doesn't change. So chalcopyrite will always, always, always have that percent composition. If I had a 100 gram sample of chalcopyrite, how many grams of copper would I have?
The same percentage.
What do you mean the same percent?
Like if you would divide the element by the sample and multiply by 100%, still give you 34.6.
Right. Because it will always be 34.6%. So if we know how much of a sample we have 100 grams. Basically we have copper. We have that number and that number. We don't have that number.
It would be 34.6 grams.
Right. We have 100 grams, and 34.6% of that 100 grams is copper. And 34.6% of 100 is 34.6 grams. Mathematically, it would just be x over 3.67 equals 0.346. Multiply that by that, solve for x. But because it's 100 grams, it's easy math. This percent literally means per 100. Per 100 grams, there are 34.6 grams of copper. Here's another one. We have a copper compound. Doesn't tell us what it is. As a whole, it weighs 1.63 grams, and we know that in that, there is 1.30 grams of copper. The only other thing we know is that the only other element in there is oxygen. We have to find the percent composition of that compound. So where do you want to start?
Finding out the percent of copper.
Let's find the percent of copper. So we've got 1.30 divided by 1.63 equals what?
0.7975.
798. is 79.8%. That is copper. Now what can we do?
Try out the numbers.
Right. We know the percent have to add up to 100. There's no other choice. And it tells us the only other thing in here is oxygen. So whatever is not copper has to be oxygen. So 100% minus 79.8% equals what?
20.2%.
20.2% oxygen. And you're done. It just took a little bit of thinking to realize I can just subtract my percent copper from 100 to get oxygen. Because they don't tell you the grams of oxygen to just divide. You have to use a little bit of smarts. Capiche? Okay. This is, I'm not laughing at that, I'm laughing at, it's kind of a masochistic laugh. Moles are not complicated, but they are going to be incredibly complicated for a lot of you. Okay? This is something that is going to absolutely plague you until that light bulb goes off. And when that light bulb goes off, you're going to say, how on earth did I not understand this? Okay? When we talk about molecules and atoms, they're very, very small, right? They're really small. So when I have a sample that I can hold, there are a whole lot of molecules or atoms in that sample, right? That's a very, very large number. And we don't want to have to write everything in scientific notation. We don't want to have to write 30 zeros on the end of everything. So we have to create a way that we can talk about real world numbers of atoms, but not get writer's credit. And so we use what we call the mole. 1 mole is equal to 6.022 times 10 to the 23rd particles. And when I say particles, I mean anything. You can have a mole of atoms, you can have a mole of molecules, you can have a mole of desks, you can have a mole of people. Okay? Is 6.022 times 10 to the 23rd particles. That number is called Avogadro's number, and it is on the cheat sheet. It is the very first thing on your cheat sheet. Okay? So you don't have to memorize it, but you're going to use it so many times you're probably going to memorize it whether you want to or not. Okay? So 1 mole of carbon is equal to 6.022 times 10 to the 23rd carbon atoms. A mole of hydrogen sulfide is 6.022 times 10 to the 23rd hydrogen sulfide molecules. A mole of copper 1 oxide is 6.022 times 10 to the 23rd copper 1 oxide units. You can have a mole of moles. That's a lot of furry rodents, right? And actually, is anyone familiar with XKCD cartoons? It's a very nerdy, very, very nerdy cartoon, okay? The same guy also has a what if series, where people pose these completely hypothetical questions and he actually figures it out. One of the questions was, if you had a mole of moles, how big would it be? And he figured it out based on the gravitational pull of all of this stuff, that a mole of moles is about the size of the moon. So you can imagine, a mole of atoms is probably going to be about that big. That gives you an idea of the scale, right? A mole is not that big. A mole is about that big. But when you got 6.022 times 10 to the 23rd of them equals the moon. So we use this mole as a bridge between the microscopic world and the real world. Just like I said, that way we can talk about the number of atoms in real world numbers. I can say I have a mole of water molecules in my hand. Okay? Where that number came from, that 6.022 times 10 to the 23rd, seems like a completely arbitrary number. Where it came from is Avogadro. If you look up his picture, I'm not sure if I have it in the slide or not, he's a really creepy looking guy. Okay? He reminds me of Rumpelstiltskin from the Shrek movie. Okay? He is really creepy looking. What he did is he figured out what is the atomic mass of carbon. Off the periodic table. 12. So he figured out how many grams of carbon, or how many atoms of carbon do I have to have until I have 12 grams of carbon. And he figured out he needs 6.022 times 10 to the 23rd atoms of carbon to equal 12. And the reason he did that is now this number also serves a second purpose. This tells us how many grams a mole of carbon weighs. So from here on out, we're going to use these numbers, but they're now going to be grams. They're not going to be AMUs, they're going to be grams. But because Avogadro's number is what it is, we can just go straight from AMUs into grams. So we don't have to worry about the how or the why, we just have to remember it's because Avogadro's number is what it is. So to give you an idea of how much a mole is, there are a number of things here. So you're familiar with these watch glasses, right? So you have an idea how big those watch glasses are. They're probably about that big. So if you have a mole of salt, you got that much. A mole of silicon, calcium carbonate, that's just chalk, some tin, and there's water. What is the molecular mass of water? H2O. This is something we've done before, right? You. So what is oxygen? 16, hydrogen is 1, you got 2 hydrogens, 16 plus 2 is 18. So 1 mole of water, we'll learn this later on, but 1 mole of water is 18 grams. Because the density of water is 1 gram per milliliter, 1 mole of water is 18 milliliters. So you've been working in the lab measuring things in your graduated cylinders. You probably have an idea of what 18 milliliters looks like at this point. 1 mole of water is 18 milliliters. So a mole isn't a lot, but it's something that you can hold. It's a tangible amount, right? This is really the little conversion type thing that people struggle with. Yes?
Quick question. So is that the same thing with like the carbon, like 12 grams of carbon is 1 mole?
Yes.
Okay.
Yes. So if you weighed out 12 grams of carbon in the lab, that means you have weighed out 1 mole of carbon.
Okay.
So I said a mole can be applied to anything. Okay, you can have a mole of atoms, you can have a mole of molecules, you can have a mole of desks. But if you take that item and you break it up into its parts, you can have moles of your parts. Okay? If you struggle with this, come back to dozens. A dozen is the same exact idea as a mole. Okay? A dozen is 12. A mole is 6.022 times 10 to the 23rd. You use them exactly the same. If I say I have 1 dozen eggs, how many eggs do I have? 12. If I say I have a mole of eggs, how many eggs do I have?
You have 6.0.
I have 6.022 times 10 to the 23rd. Okay? So we're going to try this question in moles. And if it doesn't immediately click, we're going to try the same exact question in dozens. Okay? If I have 1 mole of hydrogen sulfide molecules, in that 1 mole of molecules, how many moles of sulfur atoms do I have? I have 6.02 times 10 to the 23rd atoms. How many moles of sulfur atoms do I have? 1. Okay. How many moles of hydrogen atoms do I have?
2.
2. Imagine these are dozens. I have 1 dozen hydrogen sulfide molecules. Each hydrogen sulfide molecule has 1 sulfur. So I have a dozen molecules. Each one has 1. I have 12. I have 1 dozen. If everyone has 2 hydrogens, and I have a dozen molecules, I'm going to have 2 dozen hydrogen atoms. I'm just taking the number of moles or dozens of molecules and multiplying it by the subscript. Yes?
So would in that case, would you multiply the subscript by 3?
If the question was, and I think in your homework you'll have a question like this. If the question was, how many total atoms are in 1 mole of hydrogen sulfide? There are 3 total atoms. At that point, you don't care what type of atom, but there's 2 in 1, so there's 3. There's 3 total atoms, so there are 3 moles of atoms. Is that your question?
Yeah, more or less, yeah.
More or more? What actually was your question?
No, I think I kind of answered it. Like, no, you good.
Okay.
I'll go back to it.
Talked about that. So we talked about molecular weight, right? We are now going to calculate molar mass, but it is the same exact thing. You're going to add up what's up here just like you had before. But instead of getting AMUs at the end, atomic mass units, you're going to get grams per mole. This is what we talked about. That number up there is how many grams 1 mole of that element weighs. So if you want to find the molar mass of CO2, that's the 1 carbon plus 2 times 16, oxygen is 16, we get 44.01 grams per mole. That means that a mole of carbon dioxide weighs 44.01 grams. That also means if I weigh out 44.01 grams of carbon dioxide, I have weighed out 1 mole of carbon dioxide. There will be plenty of examples there. So, this is hydrogen. What is the atomic mass of a hydrogen atom?
1.0079.
1.0079. Okay? We're going to get a little bit trickier. When we come over to the molar mass, the things that are diatomic, is hydrogen diatomic? Yes. Hydrogen is one of those diatomic elements. We have to decide, we have to calculate this molar mass for the form that actually exists. And so hydrogen actually exists as H2. So what is the molar mass of H2, or hydrogen, going to be?
2.
Basically 2. Okay. The atomic mass is 1, but in each molecule there are 2 of them. So the molar mass is 2 grams. Same thing with oxygen. The atomic mass is 16. So what is the molar mass? 32. if you're dealing with something that is not diatomic, say sulfur, sulfur is, I think it's 32. The molar mass is also 32. Yeah.
So you only, like, for the diatomics, you would, they always have a 2 subscript, so it's ×2 for the diatomic.
Correct. And so for the sulfur, or the one we're about to do now, sodium, remember there is really a 1 here, right? So you're still multiplying, but you're multiplying by 1. So sodium is, I think, 23. 23. The atomic mass is 23. The molar mass is 23. Here's a bigger one. That's calcium chlorate. How are you going to find the atomic mass of that?
Will you
You
multiply?
have to find the atomic mass for calcium.
Calcium is 40,
So, see, calcium is
40,
40. How many are there?
1.
And then we've got chlorine. Chlorine is
2.
2 of them. What is the mass of chlorine?
35.
35.
445.
0.5 equals 71, correct?
Yes.
Yeah. And then we have oxygen. Oxygen is 16.
You have like
5,
5,
6,
6, I think.
6.
How many oxygens do we have?
Like
6,
3.
6, because you gotta multiply
We
it
actually
out.
have 6, right. There are 3 in each of these units, but there are 2 units. The way this the charges balance out, we need 2 of these to cancel out that calcium. So we have to take the 3 subscript on the oxygen and multiply it by the 2 subscript on the whole thing. So this 2 got multiplied by the 1 on the chlorine, which is why we have a 2 here. So 16 times 6 equals what?
96.
What is it?
96.
And 96.
96, so 40 plus 71 plus 96, 207. So the atomic mass of calcium chlorate is 207 AMU. What is the molar mass of calcium chlorate?
207.
207. 207 what?
Well,
Grams per mole. We already did water. We said it was 18, so it's going to be 18. Sodium chloride. Somebody add sodium plus chloride. We got 23,
58.44.
58 points. So sodium chloride is 58.44. AMU, but also grams per mole. You're going to be doing this type of a thing a lot the rest of the semester. So, these are thinking questions, the type that make people's heads roll. Okay? If I have a mole of copper and a mole of gold, which one has the greatest number of atoms?
The same?
It'd be the same. Why is it the same?
because out of 100, right?
Because a mole is just a measurement of how much there is of something.
Right. The mole is telling us how many we have. It tells us exactly how many atoms of copper we have, and it tells us exactly how many atoms of gold we have. We have 6.02 times 10 to the 23rd copper atoms, and 6.022 times 10 to the 23rd gold atoms. If I ask you, I have a dozen copper atoms and a dozen gold atoms, I have more. Obviously it's the same. It's the same idea. Okay? If I have 1 gram of copper and 1 gram of gold, which one has the largest number of atoms.
We don't want the larger atomic mass. It's kind of low.
But when you, it'd be the same because moles is the grams, right? It doesn't.
1 mole of copper weighs 63 and a half. 1 mole of gold weighs 197. So I have 1 gram of each. Which one has more atoms?
Oh,
They're the same.
No, no problem.
Somebody figured out my process of elimination. It's not gold. They're not the same. Copper.
so why would it be copper?
So let's look at this. Okay. 6.022 times 10 to the 23rd copper atoms weighs 63 and a half. 6.022 times 10 to the 23rd gold atoms weighs 197. So a mole of copper weighs less. So if I have the same amount of each, if I have 1 gram of each, I am closer to having 63.5 than I am to having 197. And so I have a larger percentage of a mole of copper than I do a mole of gold. Okay? Yes.
What was that number you said, 6.35? Repeat that.
Copper is 63.5.
Oh, okay, so it's whichever's closest to the 1 mole, which is the 6.0.
Right. Let's look at a more extreme case. It might be a little more clear. If I have 1 gram of hydrogen and gold, what is the molar mass of hydrogen? Remember, it's 2.
2, yes.
But if I have 1 gram, the molar mass is 2. How many moles do I have? I can have a decimal point. I can have a decimal. Or a fraction. I have half. If 1 mole weighs 2 grams and I have 1 gram, I have half a mole. Okay? So I have half a mole of hydrogen. For the gold, I have 1 gram, but a mole weighs 197. I certainly have less than half a mole, right? Because 1 is not half of 197. And so here, for the hydrogen, I have half a mole, so 6.022 times 10 to the 23rd divided by 2 is how many atoms of the hydrogen I have. For the gold, I have just a tiny, tiny little piece of a mole. I have nowhere near half. So because I have closer to a mole of the hydrogen, I have more hydrogen atoms.
So we compare them to the small.
Right. Okay. From here on out, you're not going to have to do that thinking, because now we're going to do the math. Okay. We have to convert grams to moles. Okay. First example, 10 grams of CO2, convert it to moles. And we are going to use dimensional analysis. This is where we start to use that crazy thing that didn't seem to make any sense, but I told you we'd come back to it. So we're going to convert 10 grams of CO2 to moles. So I'm going to start 10.0 grams of CO2. I'm going to draw my boxes. Remember this?
Mm-hmm.
So what has to be my unit here?
Gram.
Grams of CO2. Now, we're not dealing with just grams. Now we have a concept of molecules. So we have grams of CO2. We're trying to convert to moles of CO2. So I'm going to put moles of CO2 up here. You can write moles, just M-O-L. Okay? It's going to save you ES. If you want to write ES, write ES. But most people will just write MOL, CO2. So now we need our conversion factor. right? We have one number on top of the other, it's a conversion factor. So we are going to say 1 mole of CO2 weighs a certain amount of grams. And we can calculate the number of grams. That's what we've been doing. Just add up 16, or the 12 from the carbon, plus 16, plus 16 to the 2 oxygens, and you get 44.01. So 1 mole of CO2 weighs 44.01 grams. My units cancel, I'm left with moles of CO2. So it's just 10 divided by 44.01, and apparently that equals 0.227 moles of CO2. Okay. It's not hard. Take the number of grams that you have, divide by the molar mass, and you have moles.
Wait,
We can also go the other way. We can go moles to grams. So I'm going to start with 0.50 moles of CO2. What's my unit here?
Moles.
moles,
Moles of CO2. What's my unit here?
grams,
Grams of CO2. It's the same conversion factor, I've just flipped it. So 1 mole of CO2 equals 44.01 grams of CO2, and that equals 22.0 grams of CO2. Okay? Got 10.0 grams of oxygen convert to moles. What's my unit?
moles,
Grams.
grams,
Grams of oxygen. Now we have moles of oxygen here. 1 mole of oxygen weighs what?
30,
32?
32. Remember, this is the type of thing that trips people up. It's O2. Oxygen is diatomic. So 1 oxygen is 16, but we have 2 of them. So you have to use the 32. If you use the 16, your answer is going to be wrong. So you have to remember which ones are diatomic. We've got 10 divided by 32 equals 0.312 moles of oxygen.
Oh, I got 0.313.
Okay. We can take this one more step, and we can calculate the number of particles. Okay? Remember, a mole is 6.022 times 10 to the 23rd particles. This is a conversion factor that we can use in dimensional analysis. So, the question is, how much mass of magnesium chloride do we need in order to have 6.022 times 10 to the 23rd chloride ions? Okay? Make sure you notice it's asking how many 6.022 times 10 to the 23rd, which is a mole, what mass of magnesium chloride contains 1 mole of chloride ions? Okay? There's a step here that we have to do. Eventually you can do this in your head. My suggestion at this point is to include it as a step in your dimensional analysis. Okay? If you're doing dimensional analysis here, where are you going to start? What is going to be in your top left corner for your number? You only have one number, right? Got 6.022 times 10 to the 23rd chloride ions, right? If I were you, there are different orders you can do these conversions in, you'll get to the same place. My suggestion is to get from this in the moles. That way you have more reasonable numbers to work with. So let's convert the number of chloride ions into moles of chloride ions. What is my conversion factor going to be?
It's chloride ions at the bottom.
Right. So I have to have that there, right? And I'm going to moles. I'm going to go to moles of chloride. So 1 mole of chloride ions has how many chloride ions in it? If I have a mole of chloride ions, how many chloride ions do I have?
6.022.
6.022 times 10 to the 23rd. So now I've gotten to moles of chloride. But the mass I'm trying to get to is magnesium chloride. So I have to get from moles of chloride, the next step I'm going to do is moles of magnesium chloride. But I have no choice what my unit is going to be here. What is my unit going to be here? Moles of chloride ion. That has to go there. And then I said I'm trying to get to moles of magnesium chloride. What conversion factor can I use to go between chloride ions and magnesium chloride? If I have 1 magnesium chloride, if I have 1 of these MgCl2s, how many chloride ions are in that?
2?
There are 2. It's MgCl2. So for every 1 of these, I have 2 of those. So 1 of these equals 2 of those. So now I've converted moles of chloride to moles of magnesium chloride. And now we can do what we did previously. We just have to extend this. So that line is that line. Moles of magnesium chloride has to go there. I'm trying to get to grams of magnesium chloride. And 1 mole of magnesium chloride weighs how much? So magnesium, 24.3 plus 35.5 plus 35.5. 90 what? 35.21. So if you do all of this math, what do you get? Equals 47.68. And she has the right number of signals. 6.022 has 4. Her answer has 4. Yes.
So if you're like looking at the beginning here, if you just have the chloride ion, that's when you use 6.022. But if you're going in grams, then you use the mass in the periodic table. Like 1 mole of a chloride is just going to be 6.022 times 10 to the 23rd. But then if you're looking for the grams, then you look on the chart.
Correct.
Okay.
So this is saying how many of them we have. If we count them, how many would we count? Not how much they weigh.
Okay. So, and then if you have the grams, then you look at it.
Correct.
Okay.
Correct. Okay. Next thing we have to look at are the formulas that we have. And we can determine those formulas in the lab. So a couple weeks ago we did the whole take the charge and swap it with the subscripts thing to figure out what the formulas should be. But if we have a sample and we don't know what it is, we can't do that. But if we can run tests on it to figure out how much of each element is in there, we can figure out what the formula is. And there are two types of formulas. There are empirical formulas and molecular formulas. Essentially, empirical formulas are simplified molecular formulas. Remember we said if you have Na2Cl2, it gets simplified to Na1Cl1. The empirical formula is the simplified version. It is the smallest ratio of atoms that is the same ratio. The molecular formula tells you the actual number. So if you, in the lab, you do an experiment and you figure out that there are 2 sodiums and 2 chlorines, your molecular formula will be Na2Cl2, even though your empirical formula is Na1Cl1. The empirical formula and the molecular formula can be the same exact thing. If your molecular formula is already simplified, that means it is also the empirical formula. But if your molecular formula is not simplified, then your molecular formula and your empirical formula will be different. So here's an example. We have 2 compounds. C6H6, which is benzene, and C2H2, which is ethylene. Okay. What is the same about them?
Same elements, C and H.
Same elements. They're both carbon and hydrogen. What can you say about the relationship between the number of carbons and the number of hydrogens?
The place that you need
They're the
C2,
same.
C2.
It's always a 1-to-1 ratio, right? There's 1 carbon for 1 hydrogen, 1 carbon for 1 hydrogen. And so what would you say is the empirical formula of that?
CH.
CH, C1H1, right? It's simplified down to CH. What is the empirical formula for this?
CH.
CH. So they both have the same empirical formula, but they are clearly not the same thing. The molecular formula is different between them. The molecular formula actually tells you what you have. The molecular formula tells you it's 6 and 6 or 2 and 2. The empirical formula only tells you that it's a 1-to-1 ratio. This is hydrogen peroxide. What is the empirical formula of hydrogen peroxide?
HO.
HO. And this is water. What is the empirical formula for water? H2O. You can't simplify that, right? So the molecular formula is also the empirical formula. So these are just some examples. This you can simplify, right? You can divide both numbers by 5. So it becomes CH2, divide them both by 6, CH2, divide them both by 2, CH2. So they all have, these 3 all have the same empirical formula, even though they're very different things. Hydrogen sulfide, just like the water, it already is the empirical formula. You can't decrease it anymore. Calcium chloride is an ionic compound. Remember when we had the pictures of the atoms in the ionic compound stacked up, very neat little rows? When we have an ionic compound, there actually isn't a molecule in there. All that formula tells us is the ratio between them. Our ionic compound formula that you were finding over and over again is an empirical formula. That's exactly what it is. So this is saying calcium chloride is an ionic compound, so there is no molecular formula. But the empirical formula is what you would have said it was if I asked you CaCl2. So there's no way you're going to be able to count those. So we're going to skip that one. Okay? But this is CH2Cl2. There's a green one, black one, and two white ones. What is the empirical formula of CH2Cl2?
CHCl.
Is it CHCl?
Yeah.
CH2Cl2 that only.
C2H4Cl.
CHC.
We can't simplify it, right? We have two of these, but we only have one of those. So we can't simplify that. So that is the empirical formula. CH2Cl2. What about C6H3Cl3?
C2.
I mean C2, okay.
C2.
You can divide them all by 3. So C2H1Cl1. Leave off the ones. Let's come back to this one. We don't have to count it. Yeah, HGO. That's the molecular formula. What is the empirical formula? That. They're both ones already. You can't go lower than a 1. So that one. HCO2. Divide them all by 2. Let's come down and do this one. P4O6. P2O3. They're not both divisible by 4, right? You take the largest number that they're both divisible by, and that's 2. You cut both numbers in half. P2O3. Are these on your slide, the answers?
No.
So I gave you a second to write down the ones we didn't do.
Can you explain the middle one on the bottom? Yeah.
That one?
No, yeah.
That one. So it's written out in kind of an expanded form. So what you need to do is you need to condense it. You need to say, how many carbons do I have? I have 1, 2, 3. So I have C3, and then how many hydrogens do I have? I have 2, 3, 6. So I have C3, H6, which simplifies into CH2. We can take our percent composition and we can find the empirical formula from that. So we're going to go back to our chalcopyrite. Remember that any sample of chalcopyrite is going to have the same percent of composition. When we start to find the empirical formula, the first step is we have to make an assumption about the number of grams our sample is. You can pick any number you want, but I highly, highly, highly suggest that you pick 100 grams. Because if you pick 100 grams, your percentages immediately become how many grams of each element you have, right? So we're going to assume we have 100 grams. That's the first step. Now you have the number of grams for each element. You're going to convert them each to moles, which we've done. And then you're going to look at your numbers, okay? And this doesn't make sense when we actually do it. You're going to look at your numbers, and you're going to have to make them all whole numbers. If they all come out to be whole numbers to begin with, you're golden. But most likely they're not. And so we're going to have to change them into whole numbers by dividing by the smallest number and then multiplying by another number. And we'll see that when we get to it. It'll make sense. So, if those are our percentages, and we assume we have 100 grams, that immediately means we have 30.5 grams of iron, 34.6 grams of copper, 34.9 grams of sulfur. So we have to convert each of those into moles. So I'm going to start with the iron. We have 30.5 grams of iron. Grams of iron, moles of iron. 1 mole of iron weighs how much? The
55.85.
number of
55.85.
55.85. 55.85 equals what? It's 30.5 divided by 55.85.
0.5461.
61. Now we're going to do our copper. We have 34.6 grams of copper. Copper is what?
63.55.
63.55 grams of copper is 1 mole of copper. So 34.6 divided by 63.55.
0.5444.
And then we do our sulfur. 34.9. Sulfur is 32, I believe, grams sulfur. Mole sulfur. 34.9 divided by 32.
1.088.
0.88. These are clearly not whole numbers. So we have to change them. What we're going to do, we're going to look at our 3 numbers. We're going to find the smallest one. What's the smallest number? The middle one. We're going to divide all 3 of them by that number. So I'm going to take that, divide by 0.5444, which is 1, because I divided it by itself. Then I'm going to take this number. What does that equal?
1.003.
3. And then I divide 0.5444 equals 1.999. So now we have these numbers. Yes.
For that bottom one, I got a different number. Should be 1.9. 1.09 instead of the 1.088.
Oh, here?
Yeah, it should be 1.091.
I was reading out this one.
It'll be okay. It'll be okay. So, these numbers were found in a lab. These are measurements. There's error in measurements, right? Remember you eyeballed that last number. There's error there. And so, our numbers are rarely going to be exactly round numbers. So you have to decide, is this not a whole number because of measurement error? Or is it not a whole number because it's not supposed to be a whole number? Basically, if you are off by more than, let's say, 0.1, you cannot round. If your number is off by less than 0.1, you can round it to that whole number. So, what number does that look like to you? That's a 1, right? So I'm going to say that's 1, that already is 1. What number is that basically? That's basically 2. So, we've got these numbers. These are our subscripts for our empirical formula. We are done. So we have Fe1, copper 1, sulfur 2. Our empirical formula is that. Okay? The step that most people miss is dividing by the smallest one. A lot of people will find the number of moles and then say, well, these don't look like, that kind of looks like a 1, so let's make that one 1, and then do something funky with that. Make sure you divide by the smallest number first. Okay? Yes?
You said something I didn't understand off one, but I think it's.
What did I say?
You said if it's off one, you don't round, I didn't.
So imagine we did this math, okay? instead of 1.999, I got 1.87. That's too far away from 2 to say that's supposed to be 2. Okay? And I think we'll see an example, hopefully on the next slide, where this happens. Okay. So we have another one. We have cobalt. It just has copper and sulfur, and it gives us our percent compositions. First step is we have to assume a mass. What mass do we want to assume? We want to assume 100. So how many grams of copper do I have?
66.
I have 66.5 grams. 6.5 grams of copper. 1 mole of copper weighs, I think it was 63.5 grams of copper. How many moles of copper do I have? It's going to be 1 point something.
1.047.
Now I get my sulfur. I've got 33.5 grams of sulfur. Sulfur is 32. What is this? 0.047. So what's my smallest number?
They're the same.
They're the same, so pick one. By 1.047, 1.047 equals 1 equals 1. So what is my empirical formula? CUS. CU1S1. Here's another one. Shattuckite. We've got 4 elements here. Copper, silicon, oxygen, and hydrogen. How many grams of copper do I have?
48.42.
What?
0.763.
8.
Oh, 3, sorry. 763.
Silicon, 17.12. What's the mass of silicon?
38.0855.
Let's stop there. Oxygen, 4.14. Now, you're going to kill me when I do this, okay? This oxygen is not it's not free oxygen. It is not O2. It is just oxygen. And so 1 mole is going to weigh 16, not 32. Okay? You have to look at the context. Here, the oxygen is with a bunch of other things. And so we're going to say 1 mole is 16. 34.14 divided by 16.
2.133 or 34.
Will it ever be, well, I mean, it was 2 in the other cases, but like, would it be worded differently or something if we needed to do 2? Or is that
In
not?
empirical formula, it will always be 1 because it's
Okay.
going to be, unless it asks you what is the empirical formula for oxygen.
Then that's 2.
That'd be 2, but that's not valid.
Okay.
That's a dumb question.
Okay.
And the last one we have is hydrogen. We have 0.31 grams of hydrogen. this is not diatomic hydrogen. So what is my mass? We'll just call it 1. So this becomes 0.31. What's my next step?
Divide by the lowest number.
Divide by the smallest number, which is that one. 0.31, that one becomes 1. What is that? 0.884 is that.
$1.965.
2.461. Is this number correct? I just want to make sure before we.
It would just be 6.
It is? So that's going to make it more difficult. Okay. Because if we look, that one's 1, right? That's 2. That's not 2. That's not 3. That's basically 2.5. Okay? So we're going to have to do something with that. That
Can't go up.
6.
That's a close enough.
It's-
That's 7.
it's not close enough to be 7.
Oh.
So what I'm going to do, do you have the answer? What do they have us do?
There's the 7 right there. 7 moles. It's like rounded up to 7.
They do.
That one's
Because
2.9.
you're 1.008 and one is
Okay.
different. I think.
So, and this one, I said if you're off by more than 0.1, you can't round. Okay? In this situation, we're going to have to. On a quiz, on an exam, if you want to know whether it's safe to round, you can ask me. Okay? So, we said that one's 2.5, that one's 2, we're going to say that one's 7, that one's 1. But that one is clearly 2.5. We cannot have a subscript that's 2.5. So we have to multiply that 2.5 by something else in order to get it to a whole number. What can you multiply 2.5 by to get a whole number? 2. If I multiply 2.5 by 2, I'm going to get 5. So I can't just multiply that one by 2. I have to multiply them all by 2. So this becomes 5. That's 2 times 2 is 4. 7 times 2 is 14. 1 times 2 is 2. So what we end up with is copper 5, silicon 4, oxygen 14, hydrogen 2.
Why did you multiply by 2?
This one was 2.5. We have to have whole numbers. And so I said, what can I multiply 2.5 by? That's going to give me a whole number. If I multiply 2.5 by 1, I still have 2.5. If I multiply 2.5 by 2, I have 5. That's a whole number. If I multiply it by 3, I'm going to have 7.5. So that didn't accomplish anything. So if I had to multiply it by 2, then I have to multiply everything else by 2 also.
So depending on the decimal number you get, is the number you multiply by to get your whole number.
Right.
So in some cases, it could be 3 or 4.
Right.
Right.
So if this came out to be 2.33, what do you think you have to multiply by? 3. 0.33 is a third. So you're going to have to multiply by 3. You have to multiply each of them by 3. Or if you got,
What if it's 3, in this case, we got only 2?
say it again?
It's 3, which means case, it's gonna be only two, it's not gonna be like 2 point something, right?
In this case, 2.33, are you saying is, you can just round it to 2?
Yeah.
3.33 is too far away to round. So in that case, if you weren't sure if you can round, you would ask me.
No, like, exactly, because it's too far away to round it, so we're just gonna take two, no?
No, we can't take 2. We have to multiply it by something. If I take 2.33 and multiply it by 2, what do I get? 4.66.
No, I'm not talking about multiplying, I'm talking about taking, like, it's like in the second, like, yeah, we don't round it, we take only 2 points.
So it's, yeah, you
You
can't,
can't round it because it's not,
It's too far away.
it's too far away to round
if
to
it was,
3.
if it
or
was
to
2.1 though, it'd be
Exactly, that's
10,
what I'm
right?
talking
Yeah.
about.
It's too far, so
Yes,
you have to
too far.
times it to
So you have to get the whole number because you can't stay with the decimal.
Oh,
Like that.
okay. I thought we were talking about the same thing.
But if it was 2.1, you could do 2, right?
Yes.
Okay.
What is
Does
the
that help
rounding
you?
error then?
If it's
Sorry.
2.1, you could do 2, but if
Point
it's
one.
anything
If you're less
above,
than
in
0.1,
between
you're certainly
2
safe.
and 8?
Okay.
Okay.
2.85.
Oh, yeah.
Okay.
Yeah, no, thank you.
Mm-hmm.
To me, I saw that 0.1, that's off by 0.12, that's an 8. And so I would saw that and I thought, well, I can multiply by 8. But then if I multiply this by 8, I wasn't gonna get a right. And so that's why I realized that they were rounding larger than I was. If you're less than 0.1, you are always safe to round. If you're questioning, ask me, okay? Normally that decimal is going to look like a number you recognize. It's going to be 0.25, which is what? A quarter. So you're going to multiply by 4. It's going to be a third. It's going to be a half. It's going to be something that really stands out and says, I'm meaningful. Okay? I didn't mean it as a joke.
So like you said, 2.33 would be times by 6, you said?
3.
Or 3? So we would get the same answer?
No.
Oh,
So if
or are they just bigger numbers? or
so I would multiply it by 3 so that I'd end up getting 7. That's 2 times 3 is 6. That's 7 times 3 is 21, and 1 times 3 is 3.
Would they be all 7? Well, 7.
It can't be, that can't be simplified.
Or like copper now, it's like 5 down there at the bottom. The final answer,
Oh,
I'm asking.
the final answer would now be,
7621.
yeah, it'd be 7, 6, 21, 3.
When you multiplied 6.884 by 3, like it comes out to 20.6, but you round it to 21.
I rounded that to 7 before I multiplied. If I make a question, okay, on a quiz, I am not going to have it come out to be 6.88, okay? That's too fuzzy, okay? That's too fuzzy for me, okay? That's far too fuzzy for me to expect you to do.
But even though it was 0.1, like you couldn't round it to 7, no. So how did you?
Because based on my initial rule, I said 0.1. But then I realized in this case, I had to round even though it was more than 0.1.
But
So-
it's the same thing, because when you look at the second one next to the 8 is an 8, and since if it's above 5, so you add 1 to the second one. So it's going to be the 8th one, it's going to go to the first 8, it's going to be 9, so basically it's 6.9.
Yes.
And then that's when you round it to 7.
Okay.
I mean, that's the math that I know.
Right. So if you do that rounding, it works out. But there's no good reason to round there, though.
I mean, because it was the same thing that we did to the 2. We said it's 2.5 because it was 4 and 6. And the 6 goes to the 4 and it's 5. So
Right.
that's-
If it works for you, it works for you.
What is that element? What is that? Or
Shattuckite?
Yeah.
It's I don't know what it looks like. We can look it up during break if you want.
Okay.
It's not something you'll see in lab, that's for
Okay.
sure. Let me look, take a look. Let's take our break now. We'll start at 35 after on that clock. You can eliminate the other ones. Look at single concepts, and then have massive eliminate. The other ones are automatically. So now we're going to check each and not Yeah, the only thing you're missing is indicate the molecule polarity. Right, so you can just write them down. These chlorines, they're all chlorines around it, right? So they're all the same, and they're equally spread out. And so they actually balance each other. Well, it does have to do with electronegativity, but because they're all chlorines, they automatically have the same electronegativity. If that was a bromine, and you had two chlorines, then they'd be polar, because then they don't mix. You're shedding, right? So, if we're drawing the shape, your sketch is the shape. What I want to see is more of a two-dimensional representation. And so, remember,
Pretty.
We don't draw it like,
I wish I brought food.
right. So you can draw with the line, or you can draw it with the dot. But you need to think in three dimensions, know what shape is it. So what was the parent? How many things are on the picture? That lone pair system. So there are four things. So what is the parent structure if there are four?
It makes a lot of sense.
Right? So you need to picture what the tetrahedral looks like. You've got the three at the bottom forming the pyramid, and the one sticking up the top. Right? So what I would do is I would draw that pyramid. I would draw nitrogen, and then draw three chlorines on the bottom, and then draw the lone pair on top. Okay?
so the nitrogen on top, or did you just say?
You still got nitrogen in the middle, right? Then the best that you can, you're going to draw in three dimensions. You're going to put three chlorines down there.
What is right?
A line means one pair of.
Okay, so we can draw like that, or like that, like the two dots.
Right.
Okay.
Right. And then I'm going to put my two dots. But in the shape, we ignore them.
That's not true.
And so I basically erase them. So I draw that.
Okay.
So I drew the parent structure, and then erased the lone pairs across those points.
Okay. So you have to draw this.
Right. So that is showing in the shape. It's in three dimensions, not two dimensions.
Okay.
And the last thing is you have to indicate molecules of polarity. those chlorines cancel each other out. In this case, they don't, because they're all on the bottom. There's something that if it was in two, you had like that. They were all flat. Right. Well, they would all be in line. Nitrogen is here, chlorine, chlorine, chlorine. Then they're all in the same plane. So they cancel each other out. But here we have a nitrogen, we have chlorine, chlorine, chlorine. So even though they're in the same configuration of thirds like that, they're all in line. And there's nothing there. And so it's both. The quiz will be $37. We'll go through. So, but to do that, you had to draw the fluid structure that you did. So you got C2H4. So that's correct. So you just count what you have. You have 1, 2, 3, 4 single bonds and a double bond.
Oh, okay, okay. Okay. So, this one, I got,
There's something wrong with that. What's wrong with that?
is not a double.
How many electrons does this oxygen? Only has 6. Has 8. This one, 8.
Okay, so that one was, okay. So they all have that.
They all have to have 8. Hydrogen has to have 2. Everything else has to have 8.
And this one,
Yeah, so that's exactly what I just said. They all have to have 8, except
okay, okay. Thank you.
just right that it's not.
Okay. Okay, thank you.
Do you have your homework? I'm wondering if I told you something. Is this the homework?
Yeah.
Oh, no, you're okay.
What you
It
want?
must have been. I was thinking that.
Oh, okay.
You're okay.
So, okay, if we have to add something today, so this is we can write this. Which
Oh, so sweet. This is pointing out the direction. So you don't want that. See, you kind of see the positive there? That's saying the positive. Cross that.
Quick question. If I know if it's a polar and non-polar molecule, is the only way to figure that out is to like how imagine cutting it in half, that's only 10 mils. So like this, I cut it in half, so it's not equal to its polar. Okay. Perfect. Because I was paying out, because I like going to China something, so I was to.
I think I just changed the wording to be which one is the matter. It's the same.
That's not okay.
What are you gonna do tomorrow? So, one.
Nah.
No.
Oh, you looking up for it?
Okay, I was,
Should we get out of here
I was
now?
like picturing that one. I guess.
I was gonna go to it, but I was like, it's too late, just trying to.
You have to look at since you're a number, you can divide all this up here by.
Okay, got it. Thank you.
You got cheat though.
Okay.
Cheat, you don't-
So we've done empirical formula. The next step is molecular formula. And kind of like the VSEPR shaped question, where it seems like an easy question, but in reality you have to do 5 steps to get there. Molecular formula questions like that. If the question asks molecular formula, you're going to have to do empirical formula first. Okay? So we come back to our 2 molecules. We got benzene, and I misspoke earlier. Earlier I called this ethylene. It's actually ethine, which is the same as acetylene. Ethylene is what makes fruit ripen. This is not that. Okay. So this is benzene. This is acetylene. We said they had the same empirical formula, but they have different molecular formulas. If we think about the mass of this versus the mass of that, how much heavier would you say that molecule is compared to that? 3 times, exactly. That, 3 times that, right? 3 times 2 is 6, 3 times 2 is 6. So this has a mass that's 3 times bigger than that. That is not a complicated idea. So when we get to the problems, don't make it more complicated than that. Okay? What we're going to do is we're going to calculate the empirical formula, figure what that is, and then you will be told the molar mass of the molecular formula. So you compare the molar mass of your molecular formula versus the molar mass of your empirical formula. If it's 3 times higher, you take your empirical formula and multiply it by 3. If it's 5 times higher, you multiply it by 5. Don't make it harder than that. Okay? So, in order to find the molecular formula, we have to be given the molar mass of the molecular formula. If you're not given that, you cannot do it. You have to have that. Otherwise, you can't figure out how many times bigger it is. And so you can't do it. So, find the empirical formula, divide the empirical formula molar mass into the experimental. So molar mass of the molecular formula divided by the empirical molar mass, you'll get a number. Whatever that number is, you multiply your empirical formula by it. So here's our example. We have CH2. It says the molar mass is 42.12. There's no debating that. You're given that. what is the molecular formula? First thing we have to do is find the empirical formula. So, if I have CH2, I have to find, I'm sorry, I read this wrong. We already have the empirical formula.
Yeah.
It's CH, we have this empirical formula, it's CH2. So they've already done the little labor work for us.
Like, so when it says grams per mole, that's like the answer, right? We don't have to do this first.
We don't, we already have the empirical,
Oh,
but we have to use this, okay? So what we have to do is we have to find the molar mass of that. What is the molar mass of CH2? Carbon is 12, hydrogen is 1. 14. 14. So our empirical molar mass is 14 grams per mole. And it says our molar mass of our molecular formula is 42.12. So I'm just going to go 41.12 divided by 14 equals what?
42.
40. Thank you.
3?
Is it something very, very close to 3? Is it exactly 3?
Yes.
3. And so, that means my molecular formula is 3 times my empirical formula.
It's not 3, it's 2.9.
So, it's,
What was it?
It's 3.
the reason you're not getting exactly 3 is because carbon isn't, wait, carbon? No, 14. It's not exact, CH2 isn't exactly 14. It's 14 point something.
Ah.
And so if I had actually done the point something, it would have come out to be. So this means my molecular formula is 3 times my empirical formula. So I take my empirical formula, CH2, multiply my subscript by 3, C3H6. That's my molecular formula.
That's it?
That's it? In the future, you won't be given the empirical formula. You'll have to calculate the empirical formula. Just like you on the quiz today, where it says part A, find the Lewis structure, part B, draw the shape. This is a good multi-step question to ask you. What is the empirical formula? Now what is the molecular formula? Here's another one, potassium persulfate. We have percent composition, not an empirical formula. So we're going to have to use our percent composition to find the empirical formula. So we've got 28.93 grams of potassium. Potassium is what? 39.1.
Yeah.
39.1 grams of K, when mole K equals 9. That's sulfur, 3.72.
32.1.
That same thing?
Yep.
Yeah.
This is my next step.
Divide by
Divide by the smallest. What does that come up to?
4.004.
Now it's 4.
That is 4. That one you can very safely round. So we've got 114. So what is my empirical formula? I have K SO4. K1S1O4. So there's my empirical formula. Now I can figure out what the molecular formula is. What do I do?
Figure out. You take the atomic masses and add them together.
Right. So you find the molar mass of that.
Yeah.
What does that come out to be? 39.1 plus 32.1 plus 16 times 4.
$87.2.
Okay.
That's not what I know.
No, it's going to be bigger than that.
It's 135.2.
35.2. So my empirical formula comes out to be 135.2. My molecular formula is 270. How am I going to find my molecular formula?
You divide
Divide.
Divide what by what?
135.
270.
270.0 divided by 135.2.
About 2.
It is very, very close to 2.
It's 1.99. Yeah.
Because we started with these percentages, remember these percentages are measurements, which is where this error comes from. So, what do I do with that 2?
CO2,
Right.
sulfur, 2, and oxygen.
Right. I take my empirical formula up at the top, and I multiply all the subscripts by 2. So I have K2S2O8. That is my molecular formula. Sorry?
It's so time consuming.
It is.
Nope, there's not. A lot of them are like.
You're not gonna go to like 32 of those. We're never gonna finish.
You can also go the other way. Fortunately, going the other way is less work. Okay? If you have the empirical formula or the molecular formula, you can find the percent composition. What we're going to do is we're going to assume we have 1 mole. And we're just going to find if we have 1 mole, how much mass of each do we have? We'll divide by the total. So assume 1 mole. So here's our example. What is the percent sodium in sodium oxide? So, first of all, if I have 1 mole of sodium oxide, how many grams total do I have? Repeat the question.
22.99.
If I have 1 mole of sodium oxide, how many grams of sodium oxide do I have?
22.99.
Right. 23 times 2 plus 16. So, does that come out?
What was the question?
What is the molar mass of sodium oxide?
That's what you're asking right now.
Yes.
61.98.
62.
Somebody was saying, and I told them no.
It is 62.
No, it makes sense. No, I don't know. Okay. So Na2O is 62?
Yeah.
Yeah.
Okay. 1 mole of sodium oxide, Na2O, weighs 62 grams. Okay? Now we have to figure out, of that 62 grams, how much is sodium? So just take, sodium is 23
Yeah.
times 2 is 46. So the sodium equals 46. The oxygen equals 16, right? And so to get the percent sodium, I just take 46 divided by 62 times 100 equals what?
This was that formula we learned earlier? The
Yes.
first formula we did?
Yeah. Yep.
74.194.
194% sodium. And then for oxygen is 16 divided by 62 times 100 equals
25.806.
make sure they add up to 100, which they do, and you're okay. You now have the percent sodium. Actually, the question only asked for sodium, so we could have stopped. But we love chemistry so much with chemistry.
Oh, boy.
Thinking question. Cuprite, Cu2O. Chalcocite, Cu2S. Which one has a higher percentage of copper?
The Cu2S,
Why Cu2S?
the sulfur has a higher mass.
Sulfur has a higher mass than what?
Oxygen.
Than oxygen. So what does that mean?
So it'd be
Sulfur.
C2O.
When you see too old because it's less,
Right.
then you have more of it.
Yeah,
So, right. So if we have 1 mole of each,
that's true.
we're going to have the same amount of copper in each.
Yeah.
And so the percentage is going to be based on what we have on the bottom of our fraction, the total mass. Cu2O is smaller, because oxygen is lighter than sulfur. And so if we did the total, the copper divided by total in equals percentage, we want that to be high. That's going to stay the same, so we want that to be little. The smaller that is, the higher that's going to be. And Cu2O is lighter than Cu2S. Okay. We're done with that. Okay? We're moving on to chemical equations. All right? When we write a chemical equation, it has to be balanced. Okay? You will never, ever, ever use an unbalanced equation. Balancing the equation is part of writing it. If you have an unbalanced equation, you haven't finished writing it. Okay? In a problem, up here on a quiz, on a final, if you're given a chemical equation, if it does not tell you explicitly that it is balanced, you better look and make sure that it's balanced. Because it is fair game for them to make you balance it before you use it. Okay? So we have to figure out what we mean by a balanced equation. When we have a reaction, we're going to have reactants, the things that come together to react, yield products. We take reactants and we make products. And the number of atoms of each element has to be the same on the left and the right. We are not going to destroy atoms. We are not going to make atoms. We cannot do that in here. That is nuclear chemistry. Okay? We are not nuclear chemists. We are general chemists. So we are not going to do anything. The number of atoms on the left has to equal the number on the right. So that's what we mean by balancing. We're going to have to multiply things on the left and the right so that we have the same number of atoms on the left of the right. Having the same number on the left and the right is called conservation of mass. We do not destroy or make mass. In this class, the mass that we start with is the mass that ends. If you add a gram of this and a gram of that and a gram of that, Whatever you make better be 3 grams. Okay? The mass will never change. Don't forget about conservation of mass. It is a law. You break the law, you pay the penalty. Okay? So this is the reaction of iron 3 oxide, and when you heat it and you mix it with aluminum solid, you get aluminum oxide in liquid iron. Okay? This is how they get iron to use. This comes out of the ground, you get it really, really hot, you mix it with aluminum, and now you have your liquid aluminum that you can make things into. Okay? So that's the reaction we're going to be dealing with. Aluminum solid reacts with iron 3 oxide solid to give us aluminum oxide solid in liquid iron. So we're going to take this equation. We're going to look at how many of each element are there. We look at how many aluminums are on the left side. There's just one of them. There's no subscript, and there's no number here. There's one aluminum. We have 2 irons, and 3 oxygens on the left. On the right, we have 2 aluminums, 3 oxygens, and an iron. Would you call that balanced? No, it's certainly not. The oxygens are okay, but the number of aluminums changed and the number of irons changed. So what we can do is we can add what we call coefficients. You cannot change subscripts. No matter how tempting it is, you cannot change subscripts. You have to add coefficients, full-size numbers to the left of each thing. And so, we can't cut something in half. For the aluminum, we have 1 on the left, 2 on the right. We can't cut this in half. So what do we have to do on the left to make it balanced? We have to have 2 on the left. And we have a 2 by putting a 2 in front of the aluminum. The oxygens are balanced. The irons, we have 2 on the left, 1 on the right. What can we do to balance the irons?
We put 2 on the right.
We can put a 2 here. And then we'll have 2, 3, and 2 both on the left and the right. So that's exactly correct. 2, and then we add that 2. We added that 2, we added that 2. And now we have 2, 3, and 2. Yes.
Even though we're not allowed to change subscripts, that coefficient represents a subscript in its own way.
It represents a multiplication factor for the subscripts. And so, there is a subscript 1 there, right? We just don't write it. So if we're counting the number of aluminums, it's 2 times 1 is 2. If we put a 2 here, we would have 4 irons and 6 oxygens. We're going to do some of these. These are like the Lewis structures. They're puzzles. They're not hard, but they can be tricky. Okay? The more you do, the easier you'll get at it. You'll see the shortcuts and how to start. Okay? Here's another reaction. This is the burning of methane, which is natural gas. So we're burning natural gas to get carbon dioxide and water. If we add up how many of each thing we have 1 carbon in the reactants, 4 hydrogens, 2 oxygens, and then it is not balanced on the right. So we're going to have to balance this. When you're balancing, I strongly suggest that you use a pencil. If you use a pen, things are going to get ugly. Okay? You're going to write things, and then you're going to erase things. And then you're going to erase it again to write something else. If you're using a pen, you're not going to have any idea what you're doing. Okay. First thing you want to do is you want to look at the elements that are not hydrogen or oxygen. You want to save hydrogen and oxygen for the end. Okay? Those are going to be the wackos. Save them for the end. Balance the things that are not hydrogen or oxygen. In this case, that's carbon. Is carbon balanced here?
Yeah.
Yes. There's one on the left, there's one on the right. I always do hydrogen absolute last. So now all we got left is not hydrogen, not carbon, and oxygen. So let's look at the oxygens. If we look at the oxygens, are they balanced?
No.
No. We have, how many on the left?
2.
How many do we have on the right? We have 3. These oxygens come in pairs. It's O2. If I put a 2 here, I'm going to have 4. If I put a 3 there, I'm going to have 6. If they come in pairs, you can always only have an even number of oxygens, right? There's nothing I can do here to get an odd number of oxygens. Over here, these oxygens come in pairs also. But those come in singles. So, the number of oxygens I get from my water has to be an even number. If that is an odd number, it's never going to be able to balance over here. So the very, very first thing I do is I get myself an even number of oxygens. And I can do that by putting a 2 there. I now have 2 oxygens and 2 oxygens for a total of 4. Am I balanced? I have 4 on the right. How many do I have on the left?
3.
I have 2 on the left. So what can I do?
Add 2.
I can put a 2 there. Now I have 4 and 2 is 4. My oxygens are balanced. Are my hydrogens balanced?
No. Yeah.
Yes. I have 4 and I have 2 times 2 is 4. So when I fixed the oxygens, I also fixed the hydrogens at the same time.
Also, that coefficient counts for both the hydrogen and the oxygen.
Right. I have two waters. And each water comes with 2 hydrogens and 1 oxygen. So in this case, I killed 2 birds with 1 stone. That's not going to happen all that often. That's the steps we took. Okay. We've got potassium chlorate. KCl4 chlorate. That's your answer. 3. Chlorate's not one of the ones I didn't make you remember. I don't have memorized. That's why I had to look it up. KClO3 yields KCl plus oxygen. Okay? I always start with the metal. What is my metal here?
Calcium. Oh, no.
Potassium.
Okay, potassium.
Potassium. Is my potassium balanced?
Yes.
Yes. Let's move to the chlorine. Is my chlorine balanced?
Yes.
Yes. Is my oxygen balanced?
No.
No. What would you do as your first step here?
Add a 3.
Trying to get even number.
Try to get an even number. These come in pairs, that's an odd. That 3 is an odd number. So let's get an even number of oxygens.
So 2,
I put a 2 there.
and then 3.
I now have 6, so I can put a 3 here. Am I done?
No.
Why not?
Potassium is now off.
Okay, because I now messed up my potassium and my chlorine. So how many potassiums do I have?
2.
How many do I have here?
1.
So what can I do?
Add
Put
2.
another.
Put a 2 there. Now my potassiums and my oxygens are balanced. Are my chlorines balanced?
No.
Yeah.
Yes.
Yeah.
Yes. I fixed the chlorines when I fixed the potassiums. So now I'm balanced. So you see, we had the balanced potassium and chlorine, but then when we balanced our oxygen, we messed up what we'd already done. So sometimes you get in this loop, and you have to go back and forth a couple times before everything is balanced. Because it's possible when we fixed the potassium, we would have messed up the oxygen again. So let's do another one. We've got hexane. Hexane, C6H6, react with oxygen gas. Oops, no. All right, that would have been a big problem. H14 with oxygen gives CO2 plus water. Okay? So let's start with carbon. Is my carbon balanced?
No.
No.
No. What can I do?
Add a three in front of the second one.
Out of six.
I have to add 6.
Oh.
There's a little 1, and I need 6. So my carbons are balanced. Are my oxygens balanced?
No.
No.
No. What would you do?
Put a 6, probably.
You have to, like, wouldn't that be 6 times 2, make that 12?
You get 12 there, plus 1.
So it'd be 12, you have to put 12 in front of the H on the other side. No?
No.
There's something simple. What do we always do with the oxygens first?
Pairs.
Pairs. That's an odd number. Let's put a 2 here. And then reevaluate later. Okay? So now we have 12 plus 2 is 14.
So put a 7.
So I can put a 7 here. So now I have 14 and 14. Are my hydrogens balanced?
No.
No. I have 14 and I have
4.
4. So what can I do?
Put a 7 somewhere.
Yeah.
I need 14, right? The only hydrogens I have over here are right there. So let's put a 7 there. But uh-oh, I now have an odd number of oxygens. So I now have to multiply that
8.
by 2. So now I have 14 waters. Now let's stop and figure out where the heck we are, right? I have 14 oxygens. Plus 12 is how many? 26. So I'm going to have a 13 here. Now my oxygens are balanced. Are my carbons still balanced?
Yes.
Yes. I still have 6 and 6. Are my hydrogens balanced?
No.
No.
No, you got like 28.
28, 14.
14, yeah.
Got
Yeah, 14
No.
times 2.
14,
Yeah,
20,
14.
and 28.
28.
So I put a 2 here.
Yeah.
And carbon.
Now my carbons are unbalanced. So I'm going to put 2 here, but now my oxygens are unbalanced.
That's great, that's great.
So now I have 4 plus 14.
Wait,
Why
no,
put-
it's
no,
gotta
no, no.
be, it's gotta be 12 in front of the carbon.
Yeah.
Houston, we have a problem.
Twelve CO2s. So now I have 24 plus 14 is 38. So what's half of 38? 19. 19? So I believe that is balanced. 12 carbons, 12 carbons. 38 oxygens, should be 38 there. 24 plus 14,
38.
38. 28 hydrogens, 28 hydrogens. Okay, we're gonna stop there.
Yes.
Okay. I will not give you a balancing problem that is this hard. So, the first few slides, well, I'll go back. Last thing we did was balancing equations, and we finished it. So we're going to move on, and the next thing are the chemical reactions. And this is what the video, intro video, was on, and based on the fact that pretty much everybody got that one question right, what triple replacement reactions, you watched it, which is good. Last semester, nobody watched the videos. So we're not going to spend too much time on them, but we will very briefly go through them. So we have 4 types: decomposition, synthesis. Those are the simplest ones, because decomposition starts with one thing, then all of a sudden you have more than one thing. And synthesis starts with more than one thing, and you get one thing. So those are really easy. You don't even have a way of predicting those. I can't ask you, here's a compound, predict the products after it decomposes. You can't do that, okay? I have to give you those reactions. The single and the double displacement are the ones that are trickier for you because those are fair game. those make sense on what happens, and so it's predictable. And so I can ask you, if these are your reactants, what will your products be? So remember decomposition, we have a big thing that falls apart into multiple little things. That's easy. So you're not even able to do that. Synthesis reactions are simple again. You have multiple little things that become one big thing. And they don't have to be an element plus an element equals a compound. It could be an element plus a compound equals a bigger compound, or two compounds equals an even bigger compound. Basically, your key is you have one product. If you have one product, that was a synthesis reaction. Then we got to hit the single displacement. So in the single displacement, we have a compound. It's going to be an ionic compound. It's always going to be an ionic compound. And then we have a metal. It's just an element. When we mix them together, that metal is going to displace or replace the metal in the compound. So in this case, the zinc kicks out this, which is copper. So zinc kicks out copper to make zinc chloride, and now the copper is all by itself. The non-metal doesn't do anything. It just sits there. The metals duke it out to see who's going to be the binding partner with the non-metal. So this is an example of a single displacement reaction. You're going to do this at least 2 times in lab. I'm trying to remember, but you might actually do it 3 times. This works really, really well, so people who design chemistry labs like to use it. So you're going to do it over and over again. There's a copper wire in a silver nitrate solution. The copper displaces the silver to make copper nitrate, and then you get silver metal. Copper nitrate is blue, so this liquid started clear, and then when you made the copper nitrate dissolves in water, so as soon as it's made, it just dissolves, and you get a blue solution. You've used copper nitrate in class. It was the blue dropper bottle. And then we have silver that's forming a coating on the copper wire. So that silver was dissolved in the water, but when the copper dissolved, the silver had to come out of solution. So now we have basically silver plating. I'm probably going to come back to this, because we were talking about single displacement, so I just want to talk about the activity series. Somebody explain to me, based on the video, how we use the activity series. Yeah, Colin.
Basically, whatever metal is higher can displace anything lower.
Right. You find your metals. There's going to be one that's in the compound and one that's your free metal, the one that's off by itself. You find them both on the table. Whichever one is higher will be the one that ends up in the compound. If your free metal is higher than the metal in the compound, it will kick it out. If the one in the compound is already higher, they just sit there and nothing happens. So that's, just remember, whatever is higher ends up in the compound. If that means you have to make a switch, you make the switch. And if that means you don't have to do anything, then you don't do anything. So that is single displacement. And then we had double displacement. Double displacement, we have 2 ionic compounds, both dissolved in water, and they just switch partners. And when you switch partners, make sure you're always matching a metal with a non-metal. So here we have silver nitrate and potassium chloride. When you switch, the metal from this one ends up with the non-metal from that one, and the metal from that one ends up with the non-metal for that one. You're not going to get metal-metal and then non-metal, non-metal. So just switch them, okay? So in this case, when you switch, you get silver chloride and potassium nitrate. our double displacement reactions, there are really three subtypes of them. The first one is a precipitation reaction. This is the most common one that you'll do in lab. Basically, you'll have two solutions, you'll mix them, and you'll get a solid. I think maybe the second week when you did the chemical and physical change lab, you took 2 dropper bottles and you mixed them, and I think you got a yellow solid or something that showed up. So that's a precipitation reaction. It's called a precipitation reaction because just like precipitation outside where something basically falls out of the sky, here you get a solid that forms and then sinks to the bottom of your tube. So it's called a precipitation reaction. You can also have a gas formation reaction. Instead of making a solid that falls, you make a gas that bubbles out. In both cases, what makes it a double displacement reaction, why it's a reaction, is you're making something that leaves. Either it's a solid that falls to the bottom of your beaker, or it's a gas that bubbles out. You're making something that comes out of solution. So you're starting with 2 solutions, you mix them, and you make something that cannot be in solution. Either it's a solid and it sinks, or it's a gas and it bubbles out. The last type of double displacement reaction are acid-base reactions. We're not going to really talk about those today. They have their entire own lecture later on. So this is an example. We had barium chloride and sodium sulfate. We mixed them. They're both aqueous solutions to begin with. When we mix them, they switch partners. So you get barium sulfate and sodium chloride. These are our products over here. This is what it looks like in real life. So one of those solutions, we'll say it was the barium chloride, was down here, and then up here was your sodium sulfate. Doesn't matter which one is which. When you pour this one into that one, you get this white cloud precipitate down here. Which of our products is that white precipitate?
Sodium chloride.
Yeah, sodium chloride.
Barium,
Why is it the barium?
because it's the one that's solid, it's solid.
Right. So here it's already written for us. This says the barium sulfate is a solid and the sodium chloride is aqueous. So that means the sodium chloride is still dissolved in the water. The barium sulfate can't dissolve in water, so it forms our precipitate.
I have a question.
Yes.
Though. If it doesn't already say solid there, how do you know which one becomes solid?
I'm hoping that's on the next, right here, right here. So there are tables, okay? They're called solubility tables or solubility rules. And you're going to use that to predict which one is solid. So they're in your cheat sheet. You don't need to memorize them. What they do is they tell you, if you have this combination of a metal and nonmetal or anion and cation, is it going to be soluble? So what this is saying is that anything that has sodium, potassium, or ammonium in it is soluble. That means in a double displacement reaction, as a product, it will be aqueous. If you have a nitrate ion or an acetate ion, it will be soluble. If you have chloride, bromide, or iodide, it is soluble unless it is paired with silver, mercury, or lead. So do you see how this works? At the bottom here, these are things that generally are not soluble. So carbonates, phosphates, hydroxides, and sulfides are insoluble, meaning they don't dissolve in water unless they happen to be combined with ammonium or something from group 1, which is the hydrogen, sodium, potassium, like that. Okay? So what you have here is basically the same thing. It says compounds containing the following ions are generally soluble unless they are with these. Okay? It's pretty easy. I realize you won't have this to really look at until that quiz next week, but if your problem is reading this, I will certainly help you with that. Okay? Just know how a solubility table in general works, and we'll figure it out on Tuesday. So if we go back, we made two things. We have barium sulfate and sodium chloride. This says anything with sodium is soluble. So immediately, sodium chloride is soluble. But we can't just use process of elimination and say if sodium chloride is soluble, the other one must be insoluble. Because sometimes you're going to mix these and both products are going to be soluble. And that happens on the homework or the quiz, you're going to say no reaction. Okay? If you switch partners and they're both soluble, it's no reaction. It's the same thing if when you're doing the single displacement, you realize that the metal that's already in the compound is higher up that table, you say no reaction, nothing happens. So we have to check our barium sulfate. This says sulfates are generally soluble unless they have barium. So barium sulfate is an exception that is right on our table telling us it is insoluble. So we write barium sulfate solid, sodium chloride aqueous. Does that make sense? And switch them, write out both of your products, and then find both of them on here, and then figure out whether you need to write solid or aqueous. Whichever one is the solid will be your precipitate. So here's an example. This is a double displacement precipitation reaction. We have two solutions, lead nitrate, potassium iodide. Okay? If I switch them, if I switch parts, what's one of my products going to be?
Lead iodide.
Got. What are the subscripts for lead iodide? What's the charge on lead? 2. So iodide is going to be 2. What's the charge on iodide? Just like chloride. -1, so it's Pb1, so it's Pbi2. That's one of our products. If that's one of our products, what's the other one? Potassium nitrate. KNO3. So we have to figure out whether they are soluble. Let's start with lead iodide. Looking at that, is lead iodide soluble? Why not?
Because it says iodide except with
Right. Iodide is here. Iodide is soluble unless it is with lead. So that is one of our exceptions. So lead iodide is a solid. Is potassium nitrate soluble or insoluble? It's soluble. Potassium, anything with potassium is soluble, and anything with nitrate is soluble. So this is soluble, we write aqueous. So those are our two products. Yes.
What were you saying there's no reaction?
So if instead of lead nitrate, we had sodium nitrate, when you mix them, you would end up with sodium iodide, and sodium iodide is soluble. And so both products would be aqueous. And so instead of writing aqueous, you would write no reaction, and you can abbreviate reaction RX. Yes.
Sorry.
No. Go ahead.
Do these have to be balanced?
Yes. So if you get a reaction, and the question is asking you to write out the reaction. Yeah. So right here it says predict the products of the reaction, including their physical states, and then balance it. So we had yields that? Is it balanced? No. We have 2 nitrates here, 1 here, 2 iodides here, 1 there. What can I do to balance it? Let's start with the nitrate. What do I have to do to balance the nitrates? I have 2 here, I have 1 here.
Put a 2 in front.
I put 2 here. Now are my potassiums balanced? I have 1, I have 2. So what do I have to do? Put 2 up here. And it actually turns out when I do that, I fix the iodines at the same time. So now we have 1 lead, 2 nitrates, 2 nitrates, 2 potassiums, 2 potassiums, 2 iodines, 2 iodines. Now it's balanced. So that is the final equation. We have the reactants, we have products, we have state symbols on all of them, and it's balanced. Another example. We have cadmium nitrate and sodium sulfide. We mix them together and we get an orange precipitate. Because it says we get a precipitate, we know it's not no reaction. One of them has to be insoluble. So we have cadmium nitrate and I mix them. What are my 2 products going to be?
Cadmium sulfate or sulfide.
Cadmium sulfide and a what?
Sodium nitrate.
Sodium nitrate. So we've got our products. We have to figure out whether they're soluble. We've got cadmium sulfide. All right, is cadmium sulfide soluble based on this table? No. Why not? Because the table says no, right? It says sulfides are insoluble unless they are with one of these. And cadmium is neither of these. So cadmium sulfide is insoluble. Solid sodium nitrate we talked about earlier, that is aqueous. Are we done?
No.
No. Why not?
Balance.
Gotta balance it. Is it balanced?
We put 2 next to the next one.
We have 2 sodiums here, we have 2 nitrates here, 1 of each over here to begin with. We just put 2 there, we fix them both at the same time. Now it's balanced. We'll skip this one, you know. Switch to partners, figure out whether they're soluble. If you don't have the right answer there, you might want to write it down. Was this included in the video, or it was? It was not. Okay. Remember, the other type of double displacement reaction was gas formation. So instead of making a solid, we're going to make a gas. And I should replace this one. So in this reaction, we're mixing calcium carbonate which is chalk, with hydrochloric acid. Just going to switch partners. So you get H hydrogen carbonate, which is that, and calcium chloride, which is that. Calcium chloride is soluble. H2CO3 is soluble, but hydrogen carbonate in water forms carbon dioxide. And so you get a bubble, you get bubbles, and carbon dioxide comes out of solution. You won't see that reaction in the homework or anything. I should make a note to get rid of that. That's more difficult than anything you would see. Anything you would see, you're not going to see it. Let's put it that way. You might see a gas formation, you might form a gas in a single displacement reaction. Imagine you have, this is something you're going to do in class. Imagine that's your compound and you add zinc. Zinc is higher up the table than hydrogen, so you would kick that off. The hydrogen comes off, and you're going to make hydrogen gas. So then you get bubbles. But that's a single displacement, not a double displacement. I don't think you're going to see a gas formation double displacement reaction in homework. This is what's going on here. Calcium carbonate is also limestone. So here you have George Washington looking all great a long time ago. And nowadays he's looking kind of old. Because you have acid rain that forms acid, that makes hydrochloric acid, and it's eating away George Washington's face. Kind of looks like Indiana Jones and the Raiders of the Lost Ark with melting faces. So, like I said, acid-base neutralization is a double displacement reaction. Remember we said acids make H+, right? Bases make OH-. Put them together, you have HOH, which is H2O, water. So acid-base neutralization reactions are double displacement reactions that always make water. Any acid-base reaction will always make water. And not only will you always make water, you make a salt, meaning an ionic compound, and water. Every single time. Acid plus base gives a salt plus water. So we have calcium oxide. It says when we put it in water, it makes something called slaked lime, which contains calcium hydroxide. Is calcium hydroxide an acid or a base? It's a base. Why is it a base? It has hydroxide. Bases have hydroxide. And then it says we're going to add sulfuric acid to that. Is sulfuric acid an acid or a base? One person? Thank you. Sulfuric acid, believe it or not, is an acid. So now we're adding an acid and a base. Okay? What are our products going to be?
Salt and water.
A salt and water. Right. Right? So, well, I'm not going to. We'll cross that bridge when we get to our acids and bases in a few weeks. Here's another one. Hydrochloric acid and magnesium hydroxide. Do you know what this reaction represents? Picture might give you a little hint. Milk of magnesia is in that picture. So what do you think is going on here? Stomach acid. Stomach acid is hydrochloric acid. Milk of magnesia is an antacid. Gets rid of heartburn. When you take an antacid, like milk of magnesia or Tums or something, all that is a base. You're just eating a base that neutralizes the acid in your stomach. That's all it's doing. So here we have hydrochloric acid and magnesium hydroxide, which is milk of magnesia. What are our two products going to be? It's a double displacement reaction, right? So even if you don't know it's acid-base, or what acid-base always makes, just do a double displacement reaction. That hydrogen ends up with that hydroxide to give you water. That magnesium ends up with that chloride to give you magnesium chloride, which is a salt. You get a salt and you get water. Magnesium chloride and water. Combustion reactions are a fifth type. Okay? They don't fit into any of the other ones. They're kind of their own little thing. You're not going to be asked to predict combustion reactions. Okay? What a combustion reaction looks like is it's something plus oxygen yields something else. And you're never going to be able to predict what's on the other side. Okay? There is a generalization that I think is going to be shown here, but that's not something you're responsible to know. So, combustion reaction is just a reaction with oxygen with a bunch of heat that gets released. That's all it is. It's a reaction with oxygen from the air. So in this case, this is methane, natural gas. That's what's in your Bunsen burner. When you burn it, you're making CO2 and water. In that generalization I mentioned, if you have something that you burn and it just has carbon or hydrogen, no matter whether it's CH4 or it's C1000, H5000, you're going to get CO2 and water. But that's not the generalization you have to know. So this is what I was just saying. This is a bigger hydrocarbon. Hydrocarbon is something that has just hydrogen and carbon. This is C8H18 reacting with oxygen to get CO2 and water. The only thing that changes is they turn into a beast to balance. So those are our types of reactions. Okay? So these are the four. Which type of a reaction is that? Decomposition. Why is it decomposition?
This is just breaking down into two.
Right. You have one thing that breaks into multiple things. If you have one reactant, it can except break down. If there's one reactant, that has to be decomposition. What is this? Synthesis. There is one product. If there's one product, the only thing it can be is a synthesis reaction. What is this? Single displacement. We have a compound and an element. If there's a compound and an element, that has to be a single displacement reaction. So then what's that? That's double displacement. We have two compounds giving us two new compounds. What is that? Look at it read in formula form, not picture form. Synthesis. We have two things making one thing. What's this? Double displacement. We have two compounds making two compounds. How about that one? Decomposition. We have one reactant. All it can do is fall apart. And what is that one? Single displacement. Make sure that's not an argument. So now, let's get in the real world. What do you think that is? What type of reaction is that? I'll give you a hint. there was a solution here, and there's a solution here that's being dropped into that. No, not single displacement. Double displacement. Double displacement has two solutions that you mix. So this is a precipitation reaction. I don't know what these solutions were, but there's something in here that reacts with something in here to make a precipitate. It looks like you're actually getting two different precipitates. What it looks like is when you swap partners, they were both solids. So in this reaction, we're actually getting a yellow solid and a purple solid. What does that look like? Combustion. It's burning. If it's burning, it's combustion. Anybody know what that is? That is a pH meter, if that helps. You know, acid-base reaction. pH meters measure how strong of an acid you have. So this is just showing they probably mixed an acid and a base and the pH changed. We'll talk about pH later on. This one is really fuzzy. You have a beaker, and then there's a solution down here, and then you have a chunk of metal that's placed in the solution, and when you did that, you had a bunch of very thick, dark orange, probably very toxic gas. What do you think of that is? It's a chunk of metal in a solution. Is it decomposition? Can it be decomposition? No. We're starting with two things. If you have more than one thing, it can't be decomposition. I'll give you a hint here. We have two products. Okay? Is it a synthesis reaction? No. A synthesis reaction would have one product.
Single?
It's single displacement. Why is it single and not double? What's different between that and that?
Because you're ending with one.
Say it again?
Aren't you ending with? That makes sense in my head.
Think of not about what you're ending with, but what you're starting with. What's different between what you start with here and what you start with here?
Starting with one, and not two.
One.
You have one color.
They're not colors. Megan, what would you say?
One compound and then one.
You're starting with one compound, the solution, and one element, this chunk of metal. Over here, you have two solutions, which each one is a compound. So if you're starting with a solid and a liquid, it's going to be a single displacement. What about this? There was liquid in here, and they put a drop of another liquid in. What is that? What does that? You're making a solid that's coming out of solution. It's not soluble in water. It's double replacement. It's just like that. It's just in a test tube instead of a flask. That one? That's combustion. You're burning, right? That one, I to this day don't know what's going on. So we're going to skip that one. What about that one? That is, there's a solution here, and they dropped, it looks like a rock in it. And then you've got bubbles coming off. What do you think it is? Single. You got. There was one choice you didn't make, so you didn't guess double. We have a solution, and we have a compound. Or we have a solution, and then we have an element. I should have told you, said that. calcium or something. So if I told you that was calcium in a solution, single displacement. You have an element and a solution. What about that? Here we have an iron nail in a blue solution. After a while, we have a more or less clear solution in copper forming on the nail. What is that? Single displacement. We have an element, it's an iron nail in a solution. It's blue, so you might by now be able to figure out that that has copper in it. It's a single displacement. The iron displaces the copper, so now the iron came out of the nail into the solution. The blue copper that was in the solution formed copper metal on top of the nail. So we had iron plus, we'll say it was copper chloride. That's not balanced. Is it? Actually it is. But that's what's going on. The iron kicked out the copper had to leave, now the copper is off by itself. How about this? What is that? We have some green molecules and some white molecules. The hint here is to look at the products. The products tell you what this is. Synthesis. Why is it synthesis? There's two things becoming one. What is this? Decomposition. Why is it decomposition? You have one thing moving into multiple things. It just fell apart. That's decomposition. How about that?
Double replacement or displacement?
Single. We've got a compound and an element. The blue one kicks off a green one to make blue-green, and the green is off by itself. And then down here, it's double. The blue started with the red, the blue is now with the white, and the red is now with the green. They just switched partners. Here's another one. What's this? Synthesis. Why is it synthesis?
Because it turns into one.
It turns into one product. That's always your key. How about that one?
Decomposition.
It's synthesis or combination. This is an ionic compound. You made one thing. You made one thing. Synthesis. How about this one? What's going on here? So this is, we have a solution out here, and then we have a solid here. And in our solution, we have some of these white balls, which represent some sort of a metal ion, and then these, which represent a polyatomic anion, we'll say it's nitrate. And over here we have these, which didn't do anything. Instead of having white balls floating around, we have some red balls, and the white ones are now on the surface of our solid here. That's single. Yeah. We have a solution and an element. The element replaced the metal up here in the solution. So now you're getting this plating going on, just like we had the copper forming on the iron now. There's another one. What's this? decomposition. We're starting with one thing, we're making multiple things. Decomposition. Okay. When we do our reactions in water, we do our precipitation reactions, there are multiple ways we can write it. Okay? What we were writing up here is called a molecular equation. We write everything. But we can break that down so that we don't have to write everything. This sodium nitrate does absolutely nothing. We don't even need to write it there. What really all we need to write is that we're making silver chloride. And so we're going to write an equation saying silver plus chloride equals silver chloride, or yields silver chloride. But we have to go stepwise in order to show that that is actually what's going on and why that happened. So here in our molecular equation, we wrote silver nitrate and sodium chloride. But they're in water. They're dissolved. What happens to ionic compounds when you dissolve them in water? They're the ones that break apart. Ionic compounds break apart when you put them in water. So we wrote silver nitrate aqueous, but there really is no silver nitrate anywhere. We have silver ions and we have nitrate ions. We do not have silver nitrate. And we don't have sodium chloride. We have sodium ions and chloride ions. So in reality, once we mix them, all we have is a mixture of 4 ions. They don't have any sort of identity as a compound. We just have 4 ions. And so after we write the molecular equation, we're going to write what we call the total ionic equation. This is ionic equation. We have to write a total ionic equation, and after we write that, we can write a net ionic equation, which is smaller. So the very first step is to write your molecular formula, which we did, and then we're going to break it up into ions. Anything that says aqueous, if it says aqueous in the molecular formula, molecular equation, you have to break it into ions. And when you do that, make sure you figure out how many of each ion you're going to get. In this case, it's 1, 1, 1, 1, 1, 1, 1, 1. But imagine you have magnesium chloride, or magnesium, let's do magnesium chloride here instead. Magnesium chloride is MgCl2. So when you dissolve MgCl2, you're going to get 2 chlorines, and you put that 2 in a coefficient in front. I'm sure we'll see examples of that. So we went through, and anything that said aqueous, we broke apart. Silver nitrate became silver and nitrate. Sodium chloride became sodium and chloride. Sodium nitrate became sodium and nitrate. But silver chloride is a solid. If it says solid, if it says gas, you don't break it apart. You leave it as is. So this is our total ionic equation. Once you write this, you go through and you look for ions that are on both the left and the right as an ion. So silver is on the right, but it's not a silver ion. So there is no silver ions on the right-hand side. On the other hand, though, we have sodium and sodium, and nitrate and nitrate. If they're on both sides as an ion, they're called spectator ions. And if you find a spectator ion, you're going to go through and you're going to cross them out. They don't do anything. They just sit there and they watch. So here we said the spectator ions were our sodium and our nitrate. We're going to cross them out. So I what are my spectator ions? Sodium. It's on both sides. Let me cross that out, and nitrate, so I cross out nitrate. And when I cross them out, in order to write my net ionic equation, I just write anything I didn't cross out underneath it. So I have silver, plus chloride yields silver chloride. That's our net ionic equation. So you write the molecular equation. Anything that is aqueous, broken apart into ions, cross out what's on the left and the right, and what's left over, you write below as your net ionic equation. We're going to come back to this example. This is barium sulfate. Okay? Oh, sorry, we're making barium sulfate. We're mixing barium chloride and sodium sulfate. This is actually what they can use as a contrast dye in order to look at your intestines. You drink this and it forms that in your intestines and they can see it. So, we're mixing barium chloride and sodium sulfate. And so we first have to write the molecular equation, then we write the total ionic equation, then we write the net ionic equation. So what is the formula for barium chloride? It's a little periodic table. Barium is +2. We've got BaCl2, aqueous, and then we have sodium sulfate. What's the formula for sodium sulfate?
Na2SO4.
Na2SO4, and that's aqueous. What type of reaction is that? Look at the type of reactants you have.
Double displacement.
Double displacement. We have two ionic compounds, so it's going to be double displacement. When I swap partners, I get barium sulfate and sodium chloride. So I'm going to go barium sulfate with sodium chloride. And I'm going to have to figure out, are these soluble? Okay. I'm not going to go all the way back to that chart. You don't have it in front of you. But you know that sodium chloride is soluble. That's table salt. Barium sulfate is that white stuff that's very clearly not soluble. So we're going to say solid. Is that molecular formula complete? No. Why not? It's not balanced. So we've got two chlorines. Now we have two sodiums. We have two sodiums. One sulfate, one barium, one barium. Now it's balanced. So now I have to write my total ionic equation. So I have to go through, and anything that says aqueous, I have to break it up into its ion. So barium chloride is going to give me that's a solid, so I'm not going to break it up. Is that correct? No. Why not? Right. It's not balanced. But we don't have to really balance it again. We just have to look at what was going on up in our molecular equation. We had two chlorines. There are two chlorines here. So now that 2 shows up here. I had 2 sodiums. 2 goes there. I had 2 sodiums, and I had 2 chlorines. So we had already balanced it, so if I just bring those numbers down, it's still balanced. So that is my total ionic equation. Now I have to cross out my spectator ions. What are my spectator ions? What's on both the left and the right?
Chlorine and sodium.
Chlorine and sodium. So over here we have sodium and chlorine, and we have chlorine and sodium. So I'm going to cross these out and write what's left. That's our total, or sorry, our net ionic equation. It's not hard, there's just a lot of steps. You can't skip steps. People will skip steps. People will skip steps on the homework. People will skip steps on the lab. People will skip steps on the same exact problem on the lab exam. And people will skip steps on the final exam. Don't let it be you. Okay. Let's take our break. Is there a clock in here? Let's take a break and come back at 7:05, which is 6 minutes from now. Three cups of water is 24 ounces.
24, 30. Annual thing right there.
Oh, okay. You're correct, okay? But why is that number not here? There's a reason it's not there. There's a number that's very close to it, right?
Yeah, it's close, but
Why is that the correct answer and not that? One 60.
you see, I don't know about 60.
199. You just can't. So you did everything right, but the answer is 1 sig fig, so it's 700, not 720. Thank you. I have another paper for you. Okay. Oh, no, I guess I don't. Sorry.
We have to do this with our lab.
No, but you learned a lot.
Oh, okay. So I was gonna turn this on there, but that's for the lab, okay?
Correct.
Whole lab.
Correct.
Okay,
Start like
okay.
that.
Because Tuesday he only for this lecture from the fun. Let me see.
can say something bad in here. So, nothing else.
You know what I mean?
If you didn't turn in your post lab last week, don't forget just because we're not sitting in lab. Yes. Okay, so we ended on this slide here. These two slides, nope, three. That one, and that one are just the explanation of what we did. So I'm skipping those. This one is more difficult than anything you'll do, so we're gonna skip that one. Cross it out. Okay? That means we're on this one. Nonionic equation of potassium chloride and sodium sulfate. So what type of reaction is this? Double displacement. Got KCl aqueous plus sodium nitrate aqueous gives me what?
Potassium nitrate and sodium chloride.
Potassium nitrate plus sodium chloride. Sodium chloride is soluble, it's aqueous. Potassium nitrate, you look that up, it's aqueous also, okay? So that's our molecular equation. Then we have to write our total ionic equation. Anything that is aqueous, we have to break up. In this case, it's all of them. What are my spectator ions? All of them. Every single thing is on both sides. Because we didn't make anything that was a solid. So if I go and I cross them all off, what's going to be left? Nothing. So the reaction is no reaction. And so we really didn't, if you notice that these are both aqueous, hopefully you saw that when we did it, everything was just going to cancel out. So once you realized you made two things that were aqueous, you can immediately say no reaction. You don't have to write all the ions out and then cross them all off and then say you have nothing left. If you make two aqueous solutions, it is no reaction. So we have two clear solutions, mix them together, you have one bigger clear solution. Okay. Last thing we're going to do today, we're not going to finish today, we're going to go home a little bit early. Okay, so next week's lecture is kind of short, so we'll deal with it. So, energy changes is the last thing we're going to talk about today. Okay. Every reaction that we have also has an energy change that goes with it. Okay? When you react methane with oxygen, very clearly energy is being released, right? It's hot. Heat is energy. The energy is being released from that reaction. When we talk about these energy changes, we're going to talk about energy moving between the reaction and the surroundings. So for a flame, the reaction is the flame itself. That's the burning natural gas. The surroundings is the air. It's the beaker that you put in it. It's your hand if you put it in it. It's your sleeve when you reach over it and you catch it on fire. That is the surrounding. It's anything other than the reaction itself. If we do light a Bunsen burner over here, Jupiter is the surroundings also. Okay? We don't really care what the surroundings are. It's just everything except our reaction. Every single chemical and physical change has an energy change that goes with it. Like we had the law of conservation of mass, meaning if you start with 5 grams, you react it with 5 grams of something else, you have to get 10 grams at the end. We have conservation of energy. We are not creating or destroying energy. Okay? So, if you release energy from one thing, the same amount of energy is going to be absorbed by the other thing. So if we have a flame that releases 5 units of energy, the surroundings are going to absorb 5 units of energy. If we have a reaction that absorbs 10 units of energy, the surroundings are going to give it 10 units of energy. Energy always balances. But we can convert energy from one form to another. So just because we start with 10 units of heat doesn't mean we end with 10 units of heat. So here we have octane, which is in gasoline, right? If you burn that gasoline, you're going to get a few things. You're going to get heat, so the energy the chemical energy that is stored in that gasoline is converted into heat. Your engine gets hot. That's what we're trying to eliminate. Heat from a burning engine is lost energy. The more you can convert into making your car go, that means you'll get less heat and you get more miles per gallon. So we're making heat energy, we're making kinetic energy. When the car moves, there's friction. Friction turns kinetic energy into heat. But we also made compounds. We made CO2 and water. If we made more compounds, there's still some chemical energy left here. So we took chemical energy, made heat, kinetic energy, which then turned into more heat, and we still have chemical energy. But the amount of energy we started with is exactly equal to down here. This is saying ICE is internal combustion engine. So what this is saying is 32% of the energy that we started with gets converted into work, and work is moving something, which means moving the car. So when you burn your gallon of gas, only 32% of the energy that's in that gas actually goes into making your car go. And if you're running your air conditioner, it's probably a whole lot less than 32%, because your air conditioner uses a lot of it. Reactions can gain energy or they can lose energy. If a reaction loses energy, meaning it takes the energy comes out of the reaction into the surroundings, we call that an exothermic reaction. Exo, like exit. The energy is exiting the reaction. When we draw these energy diagrams, they're basically a very simple graph showing the energy in our reaction. So here we have on the y-axis the amount of energy. On the x-axis we just have time. So as the reaction is happening, we're moving from left to right, and the y-axis is just telling us how much energy we have in a reaction. An exothermic reaction. The reactants are up here. They lose energy, so the products are lower than the reactants. In an endothermic reaction, E-N-D-O thermic reaction, the reaction gains energy. So we start with reactants at the bottom and products at the top. So you need to be able to look at a graph and tell me whether it's exothermic or endothermic. Okay? Most reactions are exothermic. There are reasons for that we'll come across in a couple weeks. But in general, most chemical reactions are exothermic, meaning they release energy. Okay? So we have a burning balloon. It's a hydrogen balloon that got popped with a flame. Most acid-base reactions release some heat. This is a Bunsen burner that's releasing heat into that reaction, making it go. So, if we have an exothermic reaction, and it is releasing heat, the exothermic reaction is losing heat. It has less heat and less energy at the end than when it started. Is it going to feel hot, or is it going to feel cold if you touch it? So imagine I have an exothermic reaction. Okay, it's going on in my test tube. If I touch that test tube, is it going to feel hot or is it going to feel cold?
cold because it's really cold?
That is the most logical. That's what seems. Yes.
But you said it's kind of like a car gives off. I'm so confused. But if the car's giving off energy, usually it's hotter. Like if you touch the hood of your car, where your engine is giving off energy.
Right.
It's hot.
You're right. So it's very, very easy and tempting to say a reaction, an exothermic reaction loses energy, it loses heat, it's going to feel cold, right? The tricky part is your hand isn't the reaction. Your hand is the surroundings. So if you have an exothermic reaction, it's putting energy and heat into the surroundings. Your hand is the surroundings. So what you're feeling, you're not actually feeling the temperature of the glass. You're feeling the temperature of your hand, right? Which your brain interprets as the temperature of the glass. So that is hot. Okay, it feels hot because the temperature of your hand is going up. Endothermic reactions feel cold, even though an endothermic reaction absorbs heat. They feel cold. And that's because if you put your hand on it, it's sucking the heat out of your hand. So your hand gets cold. So it seems backwards. But you have to remember, an exothermic reaction is hot. Endothermic reaction is cold. If you just want to remember one example, you can figure it all out. Burning something is an exothermic reaction. And you all know whether burning something feels hot or cold, right? So if you can remember, burning is an exothermic reaction, burning feels hot, so an exothermic reaction feels hot. Okay? That's where we're going to stop. Okay? So there is one more type of reaction that we have to go over. Okay? They're called oxidation reduction reactions or redox reactions. They are the most by far the most complicated ones, but you're getting the Cliff Notes version of them. Okay? Oxidation reduction reactions can take multiple weeks to go over. Okay? We're going to do it in about 3 or 4 slides. Okay? We'll do that at the beginning of next week, and then we'll do next week's lecture. The quiz next week will be only on the stuff that you did Tuesday and today. Oxidation reduction reactions will not be on this quiz. I don't believe they're on this week's homework either. So I think we got through everything that's in the homework. If we didn't, let me know and I'll explain what we're going to do. Okay? Okay, you're good to go.
Have a good weekend. You too.
I don't know how to do this because I think I was
So do you have to remind you what you do know. Do you remember parent structures?
I have to say that. I mean, I don't remember the name.
Okay, but you remember what a parent structure is. Do you remember?
Yeah.
Okay. So for this, you have to look at your Lewis drawing, and figure out what the parent structure is. And to do that, you have to look at how many things are on that nitrogen. Each of these double bonds, or sorry, single bonds, counts as a thing. And that pair here that does nothing also counts. So there are 4 things on that nitrogen, and nitrogen is the center atom. So if we have 4 things on our center atom, the parent structure is tetrahedral. Tetrahedral is the one, we have the center atom, there are 3 coming off like a pyramid, and then there's 1 sticking on the top. Okay? So what I would do is,
Yes, that's it. Okay, thank you, dear Chip.
And so what you want to do is you want to draw the parent structure. Okay? The parent structure
You say you
is going to look like that,
oh, listen.
and then you have those electrons up here. Okay? But that's the parent structure, not the VSEPR sketch for the molecular shape. For the shape, you erase all of the lone pairs. And so you cross that off. So what's left is the sketch. Okay? And then you have to label the bond angles. The bond angles come from parent structure. If it was a tetrahedral parent structure, do you remember the bond angle? Yeah, 109.5. And so you draw a little line like that, and you just go 109.5 degrees. Then you have to indicate whether the molecule is polar or non-polar. Is that what polar or non-polar?
I don't remember.
Okay.
I mean, like,
So if it's polar, that means it is not symmetrical. Okay? So if I draw a line through that nitrogen like that, is it a mirror image?
no.
No. So this is polar. So I would just say polar.
I think that's the only one. This one. Species, compound.
Cannot be separated by a physical process. It's only one type. So there's only one element in there.
Oh,
So what do you think?
so only one element?
So there's only one element, so it's an element.
I know, okay.